All right, so the HEIST project all started in April of 2013 when there was a team of 6 of us that put together a proposal for a grant that NASA was offering. And we put together the proposal, we did an initial design, we submitted it to NASA, and then they told us in September that they were funding our design. And what we're doing now is we created an air filtration system that we're going to put on a DC-8 aircraft, and it's going to fly and collect air samples at several different altitudes in the atmosphere. And we're doing that so we can study which microbes live where and things of that nature. All right, here's the fully assembled HEIST project. If you take a look at it, the air is going to come in through the manifold right here, and then it'll go in and get split up into each individual system. And then after that, it's going to go into the filter housing right here, and then it'll go through our flow measurement system and then out the rear manifold through the back of the aircraft.
All right, so we are working on the high elevation impact sampling tool. Purpose of our project was to build a payload that could collect microsamples from within the air. Just a little background science on what we're doing. The sun heats the surface of the Earth. This causes air circulation where microbes can be trapped and circulated up to the upper troposphere where our weather happens. We're trying to find out what kind of microbes live at what altitudes and trying to figure their concentrations. So this is us in the plane, and we're going to collect the samples from clouds and other high elevation areas. Kind of why this is important. First of all, it's been done very little, so our biology team is trying to do something that we really don't know about. What is the concentration of microbes at high altitudes? After our project, this opens up doors to new science like, what do microbes do with meteorology? Does it change weather patterns? It would help us understand what weather predictions which should be. On top of which, it gives us a better idea of what is life in extreme environments. And this actually just helps out NASA figure out what we do in astrobiology. So it's really the purpose of why we're trying to figure out and why biology wants us to do it.
How's it going? My name's Nathan Berquist, and I'm going to talk about how we're getting the air into the system and how we're going to spread it out through the different flow assemblies. So this is the back of the system we're looking at right here. On the front of it is the exact same thing. We've got this flow separation, flow combination system. The way the air comes into this is going to be down here at the bottom. The air is going to be coming in from a J-probe inlet that NASA is going to be providing for us, mounts directly into the window of the aircraft, and through piping and stuff like that, it will come into our system. So once on the other side, the air will enter into the system, flow through the flow separation assembly, and whichever one we choose to open first, we will open the ball valves. The flow will go through the system and into that filter, and then pass out the back end here. And it has that gate valve on there so that we can control the flow depending on if we want to let more in or out. It doesn't matter. We can monitor that real time on the aircraft and adjust accordingly. So that's how the air comes in through the system. Pick which one we want to filter on, open that one up, let it go through, flows out the back, control the flow. Whenever we're done filtering that one, close it off, open a new one, begin testing on that one, and then we can just repeat that process 6 times, well 5 times, but 6th one is the control.
My name is Jordan Falgu, and I'm one of the mechanical engineers on the HEIST project. One of the big systems that we had to worry about when designing this project was the filter housings. We have filters that are going to be sampling microbial samples from the upper atmosphere, and we need a way that's safe and clean and sterile to house these filters for the duration of their testing, and then to keep them sterile until they're able to get back to the lab for analysis. So the way that we're doing this is we have 8-inch diameter aluminum discs of 1-inch thickness, and we have 2 of them per housing. You can see right here. What we did was we came up with a design for a filter housing where there's a filleted inlet, a hole for the air to pass through, and ridges to house O-rings. The 2 of these clamp together with bolts and hold the housing on the inside. The filters themselves are a PTFE membrane, and the membrane is a thin, papery substance which is 0.45 micron sized holes to allow the air to pass through, but not the microbes themselves. On our system here, we have 6 of these filter housings. There's one for each altitude that we're going to be collecting air samples, which is 5 distinct altitudes, and then there's one which is a control filter. This one will never be opened up to see any flow, and so it's going to serve as our baseline for biological analysis. Another primary component we had to worry about on the system was the filter meshes. Inside of these housings, we have filter meshes which support the filters themselves. And these were designed in SolidWorks and then 3D printed. They're made of ABS plastic, and we're going to sterilize them, and then they're going to support the filters. The reason that's very important to support the filters is because the filters themselves are a flimsy, papery membrane, and so the meshes hold them normal to the flow without bending or breaking or anything like that. That way they stay in a good form to take in lots of air samples for the duration of testing. And if you want to get a nice little close-up view.
All right, hi everybody, I'm Chris Petrie. I'm a mechanical engineering student. And this is our senior design project right over here on this rack. Basically what we have is we have some filters in there that are going to sample some air in the upper atmosphere. What we have here, as you can see, we have a flow assembly that we have taken out. Basically what we have is we have unions on either side of the filter housing, which they will unscrew and provide for easy access to take the filter out and bring it to for data collection. So we have them on all these. You just unscrew them right here, and this pops out, and you can pop one out and pop a new one back in for another experiment. So after our filter housing, we have to measure the flow rate coming out of the filter. So the way we accomplished that was we have 3 pipe T's, as you can see right here. In the first pipe T, we have a static pressure probe. What that is just a piece of tubing that sticks straight down into the flow and measures the static pressure of the flow. For the second pipe T, we have a pitot tube, which is just an L bent piece of tubing that sticks normal to the flow. This measures the total pressure of the flow. So using the static pressure and the total pressure, we can use compressible flow equations to calculate the flow rate based off the speed of sound. And the speed of sound is calculated using the last pipe T we have in the back. It has a thermocouple for measuring temperature, and the speed of sound can be measured using equations involving temperature. So once we know the temperature, we can back out the speed of sound, and then using the 2 pressure readings, we can determine the volume flow rate coming out of our filter, which the biology department needs to characterize all of their measurements and whatnot.
Matthew Loop, I'm an electrical engineer on the project, and this is what I made. It is basically a flow transmitter for each one of the filters. So because we're using pitot tubes, we have 2 pressure taps right here. The pressures, hoses connect from these pressure taps into each one of these pressure transducers, and we can get the pressure measurements from each pitot tube system, and it sends it over a RS-485 serial bus that connects to an RS-485 to USB adapter, and this connects to the laptop right here. So in LabVIEW, we can monitor real-time the flow of the system of each one of the filters. We can see the pressure and we can see a temperature. We need the temperature to measure the speed of sound. Okay, now I'm going to demonstrate communication between LabVIEW and each one of the modules. Each filter has its own little device right here. So I can press this button to run the module. You can see the temperature reading on the screen. There's no flow reading because there's obviously no flow through the system right now, but you can see the pressure values right here from the pressure measurements. And if I press this button, you can see there's a little LED that lights up showing that we have communication between LabVIEW and the electronics. And these circuit boards were custom made. We designed it in Eagle. There's a PIC microprocessor. Right here is a little programming header, so we can program the firmware onto the device. The microprocessor reads the values using an analog digital converter, and it transmits over UART. The UART goes into RS-485, goes to the serial bus, and then the serial bus turns into USB and goes into LabVIEW. LabVIEW reads it using visas. We had to write all this code in LabVIEW. There's 4 sub VIs. There's lower level communication VIs. There's for VI for the flow measurement, compressible flow equation, and then there's the main VI, which has all the filters. This board had to be hand assembled. We used solder paste. We put it down for each one of the components and used a hot air gun to solder the board. So this is what we made. It's a flow transmitter. It measures, I'm not exactly sure how far it goes, but it was designed to work for 2,000 liters per minute. And this is for the HEIST project.
999, 1,000, 1,001, 1,002, 1,003. I need, you have enough. How many of these am I going to do?